This video is a recap of the first exercise in the Terrain Analysis Workshop series. This is part of the Conservation Applications of LiDAR. To access this material, you'll need these instructions that can be found at the MinGeo site under the LiDAR section, looking for the workshop information, the training workshop information. Now, in this video, we'll be covering the exercise 1, where we're examining our basic DEM and talking about the DEM pre-processing that is needed for terrain analysis. And after we've calculated the primary attributes, we'll be working and calculating the secondary attributes. There'll be a later video handling interpretation. Now, your first step is to open ArcGIS and to examine add the digital elevation model from your area of interest that you downloaded from the MinGeo site, the particular tile with the terrain information, the points, as well as the buildings, the contours. And today we're going to work with the DEM. Add the DEM to your workspace. We're going to change the name of the DEM just to match all our instructions. We're going to change the name of this particular layer using the General tab. We're going to change this to just DEM instead of DEM01. DEM01 is the naming convention the Minnesota DNR and the MinGeo use for each DEM that they prepare for you based on the tile. Now, our first step is to examine some of the things that we can do with this DEM without doing pre-processing. And the easy way is to right-click on and to select Properties, and then select Symbology. Now, in the Symbology, we can do several different things that help us examine the image a little better. And I'm going to move this off to the side a little bit so you can see. We can change the color ramp to a series of colors that might help us examine the information a little more clearly, looking at the very high areas, the highest elevation as the white, and then various shades of red coming down to the various lowest on the stream bank, on the stream surface as green. Or we could use other color ramps. And so that's one way of displaying a little more information. Another is to use a hillshade effect, where we could put the hill shadows essentially into our picture. And here we're showing you the hill shadows. You can get a little idea with the hills modeled, the shadows modeled in there, what that would mean. Now, we could accentuate those, double or triple or quadruple those hill shades to try and get an effect to see where there's slight change or significant change in the digital elevation model. Generally, we'll keep that at 1 and not use the hill shade at this point. Now, the next step that we have to go through is to make sure you've got the Spatial Analyst turned on. And up in Customize, there is the Extensions selection, and you want to make sure Spatial Analyst is checked. Now, our first step using our toolbox will be to fill the sinks. Now, filling the sinks requires us to use the ArcGIS toolbox, Spatial Analyst tools, Hydrology tools. And the Hydrology tool we're going to use is Fill, where we're filling those depressions. And we'll use our DEM as our input, and we're going to send our output out to our workspace, and we're going to call that Fill DEM. And then we're going to leave the Z limit blank because we want to fill the sink completely. But this Z limit is where we would be able to partially fill it. We could fill it to 1 meter, fill it to 2 meters, and this is where we could establish some sort of precept to say, well, we're going to fill it based on 2 inches of rain on the landscape or something. So we could partially fill it. In our case, we want to fully fill all the depressions so we can look at how surface water would be routed on this particular raster. So we say OK. When that's done, we can examine the results. We can see that it's filled. And now we move on to the next step, which is filter. And our toolbox again, this time we're going to be using neighborhood, and we're going to be using filter. And this is a place where we would be creating a 3x3 window, moving window that would process across the entire raster. And we'll be using our DEM and we'll be giving it an output name. We'll call it filter DEM. And we're going to use the low pass filter and make sure we ignore no data in the calculations. Now the low pass will average and smooth it out. The high pass would actually accentuate those areas. So for example, if we wanted to go in and correct areas, that we would be able to do a high pass where we would accentuate those extremes so that they would stand out and we'd be able to identify them for perhaps correction or for some other action. But in our case, we want to smooth it out, to take the neighbors around it to plug a missing gap in the raster, for example. So we're going to hit OK. When that's done, you can see the filter is done. And we move to our next operation, which would be slope, where we're calculating how steep the slopes are within this, and it's within our toolbox, spatial analyst, surface, slope. And in this case, our input raster is our DEM again. And we're going to be putting that out to our location, which we'll call slope. So we call that slope DEM. Now we've got to pay attention to our output measure. Many times we're calculating slope, how steep the hills are, steep the various cells are, what the slope is, in degrees. But in our case, we want percent. And those are the two ways that slope is reported, either as degrees or as percent. And it's important you keep track of that, because that is very important for our analysis. Now the z factor we want to leave as 1. We don't want to accentuate the slopes. And the z factor is something that would allow us to change the calculation a little bit. Normally, if you're working with a meter DEM and you want to reproduce the slope in feet or something, you'd be able to put in a factor here of 0.3 something so that you could bring that down to different units. But you want to make sure that for most situations that this is 1. But this is how you would actually double the elevation value or divide it by 3 to move to feet, those sorts of things. So we're going to hit OK. And now we can see we've got a slope. And you can see the slope here in percent rise is fairly significant. So we get an idea of what what's happening. Now you want to remember that this is, as I said, percent rise. This is not degrees, so that you're getting an idea of the percent, and that it's possible to have something greater than 100%. 45 degrees would be 100%. So there's some situations in here which perhaps are anomalies, but that are the greater than 100% values. Now, what we're going to do is move on to the next step, which is aspect, which way the hill is facing, and that there we're using the aspect command in the spatial analyst surface, and we're still using our original DEM. We're going back to our original surface. We're not deriving a surface from another derived surface, and we want to give that an output name, and we're going to call that aspect DEM. There we've got our name, and we'll say OK. Now when that completes, you'll notice that it puts things into the 4 cardinal directions, that north, northeast, east, southeast. So it's showing of all these grid cells, all these 1 meter grid cells, that we've calculated how steep they are, the various slope in percent rise. Now we're calculating which way they're facing, their aspect. So this will be a surface we'll be using later. Now our next command that we're going to be working with is curvature, whether they're plan or the profile. And we'll go to our curvature under Spatial Analyst Toolbox Surface, and we're going to again go back to our DEM, our original surface, and we're going to give a basic output name, and we'll call that curve underscore DEM, and we want to separately name the profile and the plan, and we're going to call pro DEM and plan DEM for our output name. Now again, we're going to leave the z factor as 1, okay, because we're not trying to amplify or adjust the units. These are still in meters we're working with, so we'll hit OK to calculate the plan and profile as well as our overall curvature output raster. Now when this is done, you can see that we actually have 3 rasters created. We have our plan, okay, as well as our profile. And if you remember back to the lecture what those surfaces are and what they're useful for, you'll want to look back to the earlier notes that are within the first or second lecture on terrain analysis. Now we're going to move to our next step, which is the hillshade. Okay, it's also within our Toolbox Spatial Analyst Tools, Surface, Hillshade, and now we're going to create a hillshade. Rather than just display the DEM with the hillshade as a part of our display values, we're actually going to calculate a surface, a hillshade surface. And so we're going to take the DEM again as the input, and we're going to call this HSDE, and we're going to want to leave the default values. Now, just a minute talking about them for a second. Azimuth is where the sun is. If we're trying to show hillshade, we're saying where is the illumination from? It's 315 degrees on the horizon, so it's a little to the northwest. And then it's 45 degrees on the horizon. If you move this number down to 20 or 15, the sun would be real low. So what would be happening? More shadows, accentuated shadows. You get the idea how you could adjust those for the shadow. And then you could, again, use the z factor to multiply this to accentuate the shadows if that was useful for you. We're going to leave the default values for this. Okay? And when it's done, we have a hillshade, and you can see the surface here, the hillshade, which is quite interesting, gives you a real feeling for the nature of at least the landscape, and you get a little idea. You're seeing with the hillshade a little more clearly some of the drains, some of the ditching, and other features in the landscape. So there's many different surfaces we're using. Now what we're going to work on is the next one is the flow direction. So over in Arc Toolbox, and now we move back up to hydrology. Our toolbox, and we're going to do flow direction. Now this is which way the water is flowing. So we're going to again have to go back to our DEM, all right, and we're going to be using a output here, and we're going to call this D flow direction DEM, and save that. Now there's a number of parameters. We're going to take the defaults here, but there's a number of parameters and issues to talk a little bit about. It's not uncommon to use the filled DEM rather than the basic DEM as your input surface. For this exercise, we're using the basic DEM without the sinks filled. But very commonly, you would use the filled DEM as your input surface. And the other one that you want to think about and read the help about is the force all edge cells outward. So that, that is often considered as an option. You can read the help about it. For this exercise, we're just going to take the defaults, and we'll say OK. Okay, now when that's complete, we have a flow direction. Okay, so this is which way the water is flowing. So clearly it has to use the aspect to understand which way the water is going. So it calculates that for you, so which way the water. Now we're going to need to calculate the flow accumulation. And this is, again, we're using our our flow direction as our input. So it's a little different than the last step where we were using basic information. Now we're using the flow direction, and we're going to name this one flow accumulation DEM so we could keep that straight. It's important you use names that help you understand what you've got. Now we're going to use the defaults here, but let's talk about it for a second while it's running. That what it's calculating is the flow, we figured the direction of the water. Now we're figuring out which cell is spilling into a neighboring cell. So what we're going to be receiving here is another raster, just like the rasters we have, but in each of the cells will be how many neighboring cells spill into that. And you can see that there's some white values right at the beginning, and those white values have many cells spilling into them. So you're getting a little idea that the cells in the surface here with the higher values are where water is forming on the landscape. The stream is forming on the landscape, so that these cells have many neighboring cells spill into them, whereas something out in the middle of the field only has no cells spilling into it, or just a few. So you get an idea of the flow direction, flow accumulation. Now we want to do something a little bit different. We want to work with actually one of the derived layers where we're doing a calculation. And it's a little more extensive than our raster operations we've been doing in the simple spatial analysis in hydrology and surface. We're going to work with map algebra, and we're going to use the raster calculator to calculate the stream power index. And how we're going to do that is we're going to write a formula, and we have to do the natural log, okay, of our DEM, okay, our flow accumulation DEM, okay, and we're going to add to that 0, 0, 1, all right, so that we don't have any zero values within, it's very possible in the flow accumulation DEM that there are cells with 0. So we're going to give just a small little value to them. And now the stream power index is the flow accumulation times the slope, all right? And so we're going to need to put the slope, our slope DEM, right? And here we're dividing our slope DEM by 100, because what is our slope DEM as we calculate it? It's percent rise, all right? So we're going to divide it by 100, and then we're going to add that same factor so we could eliminate any zero values that exist in our slope. And you'll notice that I put quotes around, parentheses around, so that this value, first we're dividing by 100, okay, then we're adding the simple value, then we're multiplying this value times our flow accumulation DEM. Now we have to give that a good name, and we're going to call this stream power index, or SPI. We say save, and we're going to say, okay, now we can take a look at that, and you can see the stream power index. The high values are the light colors, and the low values are the dark colors. So you see where the slope is fairly steep, and there's quite a number of cells that have neighboring cells spilling into that, i.e. there's lots of water collecting or coming together, so that you get an idea of where there might be potential erosion, and the usefulness of the stream power index. Now we're going to use the compound topographic index, which is another calculation that we're going to do the raster calculator, and we're doing something fairly similar. So I'll set it up, but we're going to take the natural log of the value of the flow accumulation DEM, but this time we're going to divide it by the slope. So this is how it's set up: the natural log of the flow accumulation DEM plus our little factor to avoid zeros, that divided by the quantity, the slope DEM adjusted for divided by 100, okay, plus the little factor to adjust out the zeros. So we're going to send that out to a output data set. We're going to call that CTI, the compound topographic index, and we'll say OK. Now when this is done, you take a look at it and you can see a little different information. The high values here is where they're indicating wetness, where there is a fairly flat area and that the water would be accumulating. So it's a wetness indicator. It'd be an idea looking for wet land or damp land. So we're looking for fairly flat and where water is accumulating, because we're taking the flow accumulation and dividing it by the slope. Okay. Now this completes our first exercise.